Hello, and welcome to this lesson on representing and recognizing covalently bonded substances using diagrams. In today's lesson, we will learn how to represent covalently bonded substances using two-dimensional diagrams. Then we will understand the limitations of these models when representing complex covalent structures. So far, we've covered the basics of covalent bonds and how atoms share electrons to achieve stability. You have also come across different visualizations in the context of ionic substances, such as dot and cross diagrams, space-filling models, and ball and stick models. Building on this foundation, in this lesson, we will focus on visualizing covalent bonds. We will learn how to represent covalent bonds using similar methods, as well as a new method called the stick diagram. These visualizations will help us better understand the arrangement of electrons in molecules, visualize the structure of molecules, and predict their properties and behavior. Let's dive into the main content on how to represent covalently bonded substances with two-dimensional diagrams and understand the limitations of these models. In stick diagrams or line diagrams, lines are used to represent covalent bonds between atoms. Each line represents a pair of shared electrons. Take the example of a methane molecule, CH4. How can we represent this in a stick diagram? Step 1. Identify the elements involved. Start by identifying the elements involved in forming the covalent compound. We have carbon, C, and hydrogen, H. Step 2. Determine the number of valence electrons. Identify the number of valence electrons for each element. This will help us understand how the electrons will be shared. Hydrogen, H, has 1 valence electron, and carbon, C, has 4 valence electrons. Step 3. Determine the bonds needed. Identify how many electrons each atom needs for a full shell, and consequently, how many covalent bonds it needs to form. Hydrogen needs 1 more electron to achieve a full outer shell, 2 electrons in total. And carbon needs 4 more electrons to achieve a full outer shell, 8 electrons in total. This means that carbon needs to form 4 covalent bonds, while each of the hydrogen atoms needs to form 1 covalent bond. Step 4. Determine the atom arrangement. Since carbon needs to form 4 bonds and hydrogen only needs to form 1 bond, carbon will be the central atom. We need to place the carbon atom in the center and place the 4 hydrogen atoms around it. We then draw a line, representing a single bond, between the carbon and each hydrogen atom, totaling 4 lines. This is our final stick diagram. Let us now consider a more complex example such as carbon dioxide, CO2. We can follow a similar set of steps. Step 1. Identify the elements involved. Start by identifying the elements involved in forming the covalent compound. We have carbon, C, oxygen, O. Step 2. Determine the number of valence electrons. Identify the number of valence electrons for each element. This will help us understand how the electrons will be shared. Carbon, C, has 4 valence electrons. Oxygen, O, has 6 valence electrons. Step 3. Determine the bonds needed. Identify how many electrons each atom needs for a full shell, and consequently, how many covalent bonds it needs to form. Carbon needs 4 more electrons to achieve a full outer shell, 8 electrons in total. Oxygen needs 2 more electrons to achieve a full outer shell, 8 electrons in total. This means that carbon needs to form 4 covalent bonds, while each of the oxygen atoms needs to form 2 covalent bonds. Step 4. Determine the atom arrangement. Since carbon needs to form 4 bonds and each oxygen atom needs to form 2 bonds, carbon will be the central atom. We need to place the carbon atom in the center and place the 2 oxygen atoms on either side of it. Step 5. Draw the bonds. Carbon needs to form 4 bonds in total, and each oxygen needs to form 2 bonds. To achieve this, each oxygen will form a double bond with the carbon atom. Therefore, we draw 2 lines, representing a double bond, between the carbon and each oxygen atom, totaling 4 lines. This is our final stick diagram. Stick diagrams are a popular and straightforward way to represent molecular structures, using lines to depict covalent bonds between atoms. One of the main advantages of stick diagrams is their simplicity, which makes them easy to draw and understand, particularly when sketching out molecules quickly. This makes them ideal for representing large, complex molecules where showing all valence electrons would be impractical. However, stick diagrams also have notable disadvantages. They don't show which electrons are shared and don't accurately represent the relative sizes of atoms. This oversimplification can sometimes lead to a misleading understanding of the molecule's actual structure, particularly its 3D geometry, which is crucial for understanding molecular interactions. The second method we'll examine is dot and cross diagrams, which we've previously seen with visualizing ionic compounds. In a dot and cross diagram, we can use dots and crosses to represent the shared pairs of electrons between atoms in a covalent bond. This method helps us visualize how atoms share electrons to achieve stable electron configurations. Consider a molecule of water, H2O. Step 1. Sketch a stick diagram. Start by identifying the stick diagram for the molecule. Pause this video and think about what it will be for water. Welcome back! Your diagram should look something like this. Oxygen has 6 valence electrons, so needs to form 2 covalent bonds to have a full outer shell, while each of the hydrogen atoms has 1 valence electron, and so needs to form 1 covalent bond for a full outer shell. This structure achieves the correct bonding. Step 2. Draw shells. Now that we have an idea of the structure, we can start drawing our diagram. Let us start by placing the hydrogens and oxygens as in the stick diagram, but without the lines this time. Then we need to draw the electron shells for each of the atoms, and they need to overlap. This represents the sharing of electrons. Step 3. Add the covalent bonds. Where we have the intersections, we can draw the covalent bond. Each bond consists of a dot and a cross. The cross represents the electron being shared by the hydrogen, while the dot represents the electron being shared by the oxygen. Step 4. Complete the shell. We now need to add the remaining valence electrons for each of the atom. Each hydrogen needs 2 electrons to complete its valence shell. Hydrogen already has 2 electrons from the single bond with oxygen. Oxygen needs 8 electrons to complete its valence shell. Oxygen already has 2 electrons from each single bond with hydrogen. 4 electrons total from bonds. We need to distribute the remaining 4 electrons, 2 pairs, as lone pairs on oxygen. This is our final diagram. Let us now consider a more complex example, ethene or C2H4. We can follow the same set of steps again. Step 1. Sketch a stick diagram. Start by identifying the stick diagram for the molecule. Again, pause the video and try to form the diagram yourself. This is slightly more complex, so take your time tackling it. Your diagram should look something like this. Each carbon atom needs 4 covalent bonds to achieve a full outer shell. Each hydrogen atom needs 1 covalent bond to achieve a full outer shell. To satisfy these requirements, each carbon atom will form single bonds with 2 hydrogen atoms. Then, the 2 carbon atoms will form a double bond with each other. Step 2. Draw shells. We can again draw the electron shells, ensuring they overlap appropriately to reflect the structure and bonding. Step 3. Add the covalent bonds. Where the electron shells intersect, draw the covalent bonds. As before, each bond consists of a dot and a cross. In the case of double covalent bond between the 2 carbon atoms, we draw 2 pairs of dots and crosses. Step 4. Complete the shells. Add the remaining valence electrons for each of the atoms. Each hydrogen needs 2 electrons to complete its valence shell. Each hydrogen already has 2 electrons from the single bond with carbon. Each carbon needs 8 electrons to complete its valence shell. Each carbon already has 4 electrons from its bonds with hydrogen, 2 single bonds, and 2 electrons from the double bond with the other carbon. 2 pairs of electrons are shared between the 2 carbons. This means that there are no remaining electrons to draw. Let us once again verify that each atom has a complete valence shell. Counting the electrons, we can clearly see that each hydrogen has 2 electrons, while each carbon has 8 electrons. This matches our expectations. Dot and cross diagrams provide a clear and detailed representation of how atoms share electrons to form covalent bonds. One significant advantage is that they show the specific electrons involved in bonding and those that remain as lone pairs. This level of detail helps in understanding the electron distribution around each atom, which is crucial for predicting the molecule's geometry and reactivity. However, dot and cross diagrams also have their limitations. They can become quite complex and cluttered, especially for larger molecules with many atoms and bonds. This complexity can make the diagrams difficult to draw and interpret. Furthermore, these diagrams are two-dimensional representations of molecules, which can sometimes be misleading, as they do not accurately depict the three-dimensional shape and geometry of molecules. In our next lesson, we'll look at three-dimensional representations. Let's now tackle some problems. We'll start with a simple example. Question 1. Draw a stick diagram and a dot and cross diagram for a chlorine molecule, Cl2. Let's start with the stick diagram. Start by drawing the symbols for each atom involved. Here we have 2 chlorine atoms. Next, recall that chlorine has 7 valence electrons. To achieve a full outer shell, each chlorine atom needs 1 more electron. This tells each chlorine atom will share 1 electron with the other chlorine atom, giving a single bond. Let's now sketch the dot and cross diagram. We already know that each chlorine atom has 7 outer electrons, and that each of the chlorine atoms will contribute a single electron to the shared pair, giving us this structure. Let's move on to a slightly more complicated example. Question 2. Draw a stick diagram and a dot and cross diagram for an ammonia molecule, NH3. We can start by identifying the valence electronic structure of the atoms involved. Nitrogen, being in group 5, has 5 electrons in its outer shell, meaning it requires 3 more electrons to gain a full shell. Hydrogen atoms have 1 electron in their outer shell, but since it is the first shell, it can only take up to 2 electrons. This means hydrogen requires 1 more electron for a full shell. Using this information, the nitrogen atom can share an electron with each of the hydrogen atoms, and each hydrogen atom can share an electron with the nitrogen atom. This gives us this stick diagram and this dot and cross diagram. Finally, let's do a complex example that does not just have single bonds. Question 3. Draw a stick diagram and dot and cross diagram for hydrogen cyanide, HCN. We start by identifying the valence shells of each element. Hydrogen has a single electron in its outer shell and needs 1 more for a full shell. Carbon has 4 electrons and so needs 4 for a full shell. And nitrogen has 5 and so needs 3 for a full shell. Using this, the carbon atom can contribute 3 shared electrons to the nitrogen, and the nitrogen can contribute 3 shared electrons to the carbon. This gives a triple bond between the carbon and the nitrogen. The carbon is now missing an electron, which will be shared by hydrogen, so that we have a single bond between carbon and hydrogen. This gives us this stick diagram and this dot and cross diagram. In today's lesson, we delved into two-dimensional representation and recognition of covalently bonded substances using diagrammatic methods. We explored stick diagrams, where lines represent shared electron pairs. We then looked at dot and cross diagrams, which use dots and crosses to show shared pairs of electrons in covalent bonds. Throughout the lesson, we emphasized the strengths and limitations of each diagram type, and in our next lesson, we will look at more ways to represent covalent structures.